Hello, this is Dr. Jack Jackson back again, and we're going to be talking about some more discrete probability. In this video, we're going to be talking about conditional probability. This is the start of the material that corresponds to the second of my homework sets in my class. So let's kick the ball off here by looking at a table here of some comic books that this collector may have. And he collects comic books from the two major publishers, DC, which we'll denote as D, and Marvel, which we'll denote by M. And then he has these graded into one of three conditions, either good, G, fine, F, or near mint, N. And you can see how the quantity, the frequency of each of these categories. So notice that these numbers are for the frequencies of the intersection. So in other words, the 211 is for how many DC comics that are in good condition, whereas 557 is the number of DC comics in fine condition, 235 is the number of Marvel comics in fine condition, and so forth. So let's just start by doing some probabilities, not necessarily conditional probabilities just yet, but let's just review some of the kinds of probabilities that we have done in the past with a table like this. So what I'd like you to do now is to figure out these probabilities. Probability D, probability of Marvel, M, probability it's in good, G, probability of F, and so forth, as you see the ones that I have here. Now, what I'm having you find these probabilities is we're just considering that we pull one of these comic books out at random. What's the probability of D means what's the probability that you get a DC comic when you do that, and so forth. Now, to do this, you're probably going to want to add some total row and columns to the table. So go ahead and do that, and then figure out the probabilities. When you do this, and then when you're ready to go on, come back. Press pause now. Well, the first thing that we're going to do is to add some totals to this. So 211 plus 133 is 344. 557 plus 235 is 792. 320 plus 502 is 822. And if you add across all the DCs, you get 1088. If you add all the Marvels, you get 870. And you can get the total of 1,958 total comic books in the collection by either adding the 1,088 and the 870 to get that, or adding across the totals row here for each condition, adding the 344, the 792, and the 822 to get that. Or you can add those six original numbers that we had together all together and get that. So either way, you should get the same number, 1,958. So if you haven't done it already, go ahead and use these numbers to help us with computing these probabilities. Press pause if you need to. Okay, so let's go ahead and hopefully you've done this. And here are some of the probabilities. I have these probabilities worked out first. Notice that in every single case, the denominator starts out as the 1,958 because we're choosing that item from the entire collection of 1,958 items. And then we just have to figure out what the numerator is. We'll reduce the fraction when it's possible. And I've also given it in a percentage form rounded to the nearest hundredth of a percent. So for example, the probability that it's a DC would be the 1,088 over 1958, which reduces to 544 over 97, or a little over about 55.57%. The probability that's in fine condition would be the 792 over the 1958. That reduces to 36 over 89, or about 40.45%. Now, whether you call this G and M or G intersect M, it needs to be both good and Marvel. Well, the ones that are both good and Marvel, there are 133 of those. We're still choosing from the total group, so that's 133 over 1958, or about 6.79%, and so forth. I'll let you look over the rest of these yourself. Let me do one more. The OR probability is a union, so whether you call it the probability of D or F, or the probability of D union F, that's the same thing. So a DC, or fine. So those would be all the ones on the DC, these three cells here, plus the fine one here. Now we've already totaled up those three, so that's 1,088, and we add the 235, that's 1,323 over 19, and then of course that'll be over 1958 for the probability of about 67.57%. Now you could also do it by adding 1,088 and the 792, but then you'd have to subtract the 235 because you don't, otherwise it would be counted twice. That 235 is counted in that 792, and it's counted in the, I'm sorry, the 557 is one you got to watch out for. The 557 is the one you'd have to subtract because it's counted in the 792 and in the 1,088. So either way you do that, you should come up with that same amount. So just take a look at those and see if you can see what's going on there. And this type of table is called a cross-tabulation table or contingency table. Okay, now what I'd like you to do is to basically take this same table, and instead of putting frequencies in all of these, put relative frequencies, and they're relative frequencies as percentages of the total amount. So see if you can convert this to a relative frequency table. Go ahead and do that now. Press pause. Well, here's the original table up here with things made into frequencies, and the one on the top does those frequencies in exact form in fraction. They're not reduced in every case there, but notice that those are actually probabilities then of drawing one item that's in that category when you're drawing the one item from the total. You see the same information in the second table in percentage form with rounded off. So exact values are in the top version of the table. The second version is rounded off data. Okay, now notice that the stuff here on the bottom row, whoops, back up. The stuff on the bottom row here that's shaded with a kind of tan background, those are the total number of good, fine, and near mint. So those are the probabilities of those three things. These two over here that are shaded on this side, on the far right side in that total column, are the probability of the DC and a probability of a marvel. Those probabilities are called marginal probabilities. They're the probabilities on the margins. These that were basically corresponding to the original numbers that we were given, the frequencies of these intersection things, are probabilities of intersection. So the 12% is a probability that it's fine intersected marvel and fine. Okay, so these problems that are with the green background are called joint probabilities. All right, well that's really kind of a review. We've done that before. But now let's change it to something slightly different, and this is going to be a conditional probability. Now suppose that we randomly choose a comic, but it turns out that we know it's a Marvel comic. And we want to know what is the probability that it's in near mint condition. So notice that I'm giving you a little bit more information here. I'm not just saying it was chosen from any of them. It is, I've told you some extra information. It's a Marvel comic. Does that change your estimate or exact value actually of the probability? Or equivalently, another way to say the same thing is, if we're choosing a random comic just from the Marvel comics, and we want to know that the probability that it's in near mint condition. This is what we would say is the probability that it's in near mint given that it's a Marvel comic, or with our abbreviation letters up there, that's the probability of N given M. So M is the thing we know. We know it's Marvel. That's the vertical line is like such that or given that. Okay, so what's the probability that it's in near mint given that we know it's a Marvel comic? And so what is it in this particular case? See if you can figure that out. Okay, you got it worked out? Okay, so we basically know that it's chosen from the 870. So now this time the denominator is not the 1,958. We've narrowed it down to the 870. So basically what we've done is we've kept the Marvel row, and it'll just sort of throw away the rest of the table. And so if that time the total is 870, so that's the denominator. And of those, the ones that are in near mint is the 502. Now remember, the 502 is not the total near mints, but the near mints that are already Marvel. So the numerator then is what? Well, it's near mint intersected Marvel, and the dividing by just Marvel. So anyway, it's 502 over 870, or in decimal or percent form, that's approximately 57.70. So we're basically ignoring the table except for the Marvel row. Now, what would it be if we flip it around? What would be the probability of Marvel given it's near mint? Okay, so what is the probability of a Marvel given near mint? Go ahead and figure that one out now. Well, hopefully you've figured it out, that what we're doing this time is we're basically keeping the near mint column and ignoring the rest of the table. So this time the total is 822 and the numerator is 502. So it's 502 is the amount we know it's near mint. How many of those are Marvel? 502. And so the relative frequency there is 502 over 822, which is the probability that we draw one that is near mint if we're drawing just from the Marvels. That reduces to 251 over 411 and exactly and approximately 61.07%. So remember that when we're doing just basic probability, we're choosing from the entire sample space, from the full collection, and no additional information is provided. So we can, at least if it's a finite sample space, we can have the relative frequency as the probability. So the probability of the event is the size of the event divided by the size of the sample space. And the denominator, in this case, for this table at least, this comic book collection was the entire collection of 1,958 comics in the sample, and that was the denominator. That was the first set of probabilities we did. But then when we do conditional probability, at least for a finite sample space, they apply when we're choosing from a subset of the entire sample space. Okay, in other words, we're choosing from some sub-collection, or equivalently, we're given some additional information. Not that we're choosing just from anything, but we know some information. And when we do that, that modifies our probability. So the relative frequency of the intersection as a part of the given set is the probability of A given B. So the probability of A given B is the size of the intersection, A intersect B, or A and B, divided by the size of B. So notice the one after the vertical line is the one we know has happened, and that's going to be our, sort of replaces our sample size as the denominator. So we're restricting our attention to only the stuff where event B happens. It's like restricting to a single row or a single column in our table, like we were looking at before. So here we go. Let's do some conditional probabilities. So practice with the same table. Here are a bunch of different ones. Do the probability that we chose a good comic, good condition comic, given that it was Marvel. Do the probability that it was Marvel, given it was a good condition. Probability of near mint, given Marvel. Probability of near mint, given DC. Probability of DC, given near mint. And probability of Marvel, given near mint. So go ahead and figure out all 6 of those conditional probabilities now from the table. Press pause, come back when you're ready. Press pause now. All right, well, here we go. So here are the answers. Hopefully you're checking out with these just quite well with what you're doing. So the probability of good given Marvel, we're dividing by Marvel. We know Marvel happened, so we're down to the Marvel row, the red row here. And so we know there are 870 total to choose from, and of those we're choosing the ones that are in good condition, so the ones that are good and Marvel, which would be the 133. So that exact probability is 133 over 870. That, as a decimal approximation, that's about 15.29%. How about Marvel given good? Well, now that we're choosing from the good ones, which is a denominator of the size of the good events, good comics, which is 344, and the good intersect the Marvel, is, again, 133, so that's the numerator. So here we have 133 over 344, or 38.66%. So in other words, we're saying about 39% of the good comics are Marvel, and about 15% of the Marvel comics are good. Notice, by the way, that those are two different things. Probability good given G given M and M given G are not the same. Probability of a near mint given Marvel would be the size. Well, let's look at the denominator first. We know it's Marvel, so we're restricting to this row. We divide by 870, and we want the ones that are near mint and Marvel for the numerator. That's 502, and so it's 502 over 870 reduces to 251 or 435. So either one of those is your exact value. There's the reduced fraction form, and approximately is 57.7%. Let's reverse it. What about Marvel given near mint? That's down here in the bottom right. So now we know it's near mint, so we divide by the size of the near mints, how many we have, which is 822. And the numerator is the ones that are Marvel and near mint, which is 502. So that's 502 over 822. That reduces to 251 over 411. That's the exact value of the probability, or approximately 61.07%. How about near mint given DC? Okay, given it's DC, we know that's 1,088 of those, so that's the denominator. The numerator is going to be where it's of those, the ones that are near mint, which is this 320. That's 320 is D intersect N, or N intersect D. Okay, so 320 over 1,088 reduces to 5/17, or about 29.41%. Reversing it, D given N. Okay, so we know it's near mint, so we're dividing by the 822, and the numerator then is near mint given DC. That's going to be 320. That's 320 over 822 reduces to 160 over 411. That is the probability of D given N, the probability it's a DC given we know it's a near mint, and that is approximately 38.93%. And once more, notice that switching the order of these things does make a difference. Now, if the sample space is finite, then we've seen that the probability of A given B is the size of A given B, A intersect B, over the size of B. Well, if we divide numerator and denominator by the sample space, then this top, the big numerator here, becomes the probability of A intersect B, and the denominator becomes the probability of B. So even when it's not a finite sample space, we can still use the last version to make sense. And so we're not like trying to divide infinity by infinity or something. So it does work out, and so this is the final version you see at the bottom here is actually the definition of conditional probability of A given B. So the probability of A given B by definition is the probability of A intersect B divided by the probability of B. Notice once again, the one that you know happened is B, and that's the probability of that is the denominator, and the probability that they both happen, that probability of A and B, or A intersect B, that's the numerator. Take this expression now and solve for this numerator here. In other words, how would you do that? How would you get rid of this probability of B? Well, it's attached by division, so we undo that by multiplying the right side by probability of B. We'll cancel that out, leaving probability of A intersect B by itself, but of course you have to do that to this other side. And so you end up with, since the probability of A given B is probability of A intersect B over probability of B, we get the probability of A intersect B is probability of B times the probability of A given B. So we can use this to find the probability of the intersection. If we first know the probability that B happens, that gives us this factor, and then once we know if B happens, we know the probability of A, given that situation, that's this conditional probability. If we just multiply those two together, we get the probability that they both happen. That's going to be a very important technique for us in terms of building up what we call probability trees a little bit later on. Now similarly, the probability of B given A is the probability of A intersect B over the probability of A. So similarly, multiply both sides by probability of A here, and we get probability of A intersect B is probability of A times the probability of B given A. Now if you notice that this one over here is the probability of A intersect B, and the one on the right is also the probability of A intersect B. We're going to use that fact and leverage it in what we call Bayesian techniques in a couple of sections down the road here. We're in a video that's coming up a little bit later on. We're going to leverage this, and we're going to work on what are called probability trees, and we'll work on two different trees. This will be in one tree and this will be in the other tree, but it'll ultimately be the same number, and that will give us a connection that we'll see a little bit later on. We'll come back to that a little bit later. So let's take the definition of what we just came up with, or we can either take the definition, probability of A intersect B equals probability of A given B equals probability A intersect B over probability B, or we could have it in this form: the probability of A intersect B is probability B times probability of A given B, or we could even solve for probability of B here as well. So you have three basically parts here, three probabilities. If we know any two of them, then we can solve for the third one. Okay? So let's do some little application problems, or just some little problems that work with that. So here are three different problems. The first one is, suppose that we know that the probability of E intersect F is 0.25, and we know probability of F is 0.6. Can you use that to find the probability of E given F? Okay, that's one problem. Another one is, second problem, suppose we know the probability of B is 0.5 and the probability of A given B is 0.3. Can we use that to find the probability of A intersect B? And finally, the third one, the probability of C intersect D is 0.25. We know that, and suppose we also know the probability of C given D is 0.45. Can we use that to find the probability of D? So first of all, tell me if this situation is possible or not, if I've given you enough information to do it, and if so, then go ahead and compute that probability. So let you think about this a little bit and see if you can work these out. Come back when you're ready. Press pause now. Well, in each of these three cases, we know three of the pieces in that definition of a conditional probability, so we can solve for the third missing piece. And here are the details worked out. So we know that probability of E given F, by definition, is the probability of E intersect F over the probability of F. We're given the probability of E intersect F is 0.25. We're given the probability of F is 0.6. And so this works out to be, 25 over 60, which reduces to 5/12, or is 0.416 with the 6 repeating. So actually, since I worked that out to a repeating decimal, both that one is a repeating decimal and that fraction at the end, reduced fraction, are exact values. The second one down here, probability of A given B, by definition, is the probability of A intersect B over the probability of B. We can solve for the intersection like we did a while ago by multiplying probability of B of both sides. And so we get the probability of A intersect B is the probability of B times the probability of A given B. Probability of B was 0.5. The probability of A given B was 0.3. Multiply it, you get 0.15. And the final variation is this one. The probability of C given D is the probability of C intersect D over the probability of D. I'd multiply both sides by probability of D to get the probability of C intersect D is probability D times probability of C given D. And then I divided both sides by, let's see, we want the probability of D is one we're looking for. So I want to divide by this conditional probability on both sides. And we get probability of D equals probability of the intersection of C and D divided by probability of C given D. And now just plug in on the right The intersection probability is 0.25. The conditional probability is 0.45. So, well, that's multiplied by 100 here on top and bottom. That's 25 over 45. That reduces to 5/9, or as a decimal, that's 0.5 repeating. And so we see that that conditional probability gives us this this definition here with 3 parts. And if we know any 2 parts, we can find the third one. Okay, so let's look at some probabilities here. Some of these are just straight probabilities. Some of these are conditional probabilities. And this is going to be, let's say we use a standard deck of cards to use as an example here. So see if you can work these out. I'll just read them to you real fast, and you work them out, come back, and check your work. The probability that we draw, now what we're doing here is we're shuffling the deck, we're drawing out a single card. So one single card drawn at random. So what's the probability that card is a red card? What's the probability it's a face card? What's the probability that's a red and a face card? What's the probability that's red given it's a face card? What's the probability it's a face card given red? What's the probability that it's a spade? What's the probability that the spade given it's black? What's the probability it's black? What's the probability it's black given a spade? How about the probability that it's red given it's a spade? The probability of a king and the probability of the king given it's a face card. Okay, press pause and work this out now. Okay, well, hopefully you're back and you've worked through this yourself. Hopefully you were able to get these without too much trouble. So the probability that's a red card, well, there are 26 red cards in the deck and there are 52 total. So that reduces, that's 26 50-seconds, or half. Half the cards are red, so half or 50%. And by the way, this asks you to give it in a form which shows the actual number of cards as a numerator and denominator, and then exact reduced fractional form, and then approximate in percentage form rounded to the nearest tenth of a percent. So there we have it in all those forms. The probability of a face card, well, there are actually 12 face cards, so 12 50-seconds is the probability, or 1/4 of them are face cards. And that is incorrect. Actually, the 12 50-seconds is correct, but I didn't reduce that correctly. Divide numerator and denominator by 4, and you get 3/13. So 3 out of every 13, out of the 13 cards in one suit, 3 are face cards. So it's 3/13, which is 23.1% approximately. Red and a face card. So there's 6 cards that are both red and face cards. So it's 6 50-seconds. That reduces to 3 over 26, or about 11.5%. Red given it's a face card. Well, there are 12 face cards, and 6 of those are red. So it's 6/12, or 1/2, 50%. Okay. The probability it's a face card given it's red is, well, let's see, there are the red ones, there are 26. 6 of them are face cards, so red and face card is 6. That's 6/26. That reduces to, that's not correct, so let's fix that. Okay, I think I have that fixed now. Let's see, where was I? Yeah. Face card given red is 6 over 26. Divide top and bottom by 2, that's 3/13, which is about 23.1%. Probability of it's a spade is 13 over 52, or 1/4, which is 25%. Probability of the spade given it's black, well, there are 26 black cards and 13 of them are spades. That reduces to 1/2, so half of the black cards are spades, 50%. Probability this black is 26 over 52, or reduced to 1/2. Half of all the cards are black. Black given it's a spade, well, there are 13 spades, and And of those 13 spades, all 13 are black. So that's 13/13ths, which reduces to 1, or 100%. The probability that is red, given it's a spade, well, there are 13 spades, and spade intersect red is empty, so there are 0 of those. So 0 of the spades are red, so that probability is 0%. The probability that it's a king is 4/52, or 1/13th. It's about 7.7%. The probability that it's a king given a face card is 4/12ths. There are 12 face cards, 4 kings, and that reduces to 1/3. So 1/3 of the face cards are kings. That's 33.3% approximately. Okay, so you should be ready to do some problems now on some conditional probability. Come back with our next video, and we're going to get into some multi-stage probabilities and a little more interesting situations with that.